Okay, so I think we're going to go ahead and get started. So welcome everyone. My name is Katie Hickson. I'm a section member at large with ISFR and an assistant professor at Dartmouth College. Thank you for joining us today for our fourth annual virtual 3-minute research pitch competition. First, I'd like to recognize the organizers and moderators. As you can see here, you'll also be hearing from them throughout the competition as well. Special thanks to Caitlin Collins for all of her hard work in pulling this together, and Mike for sharing his slides right now. Before we begin, I just want to go ahead and thank today's judges as well. So I'm going to let them each do their background. So our first judge is Dr. Caitlin Collins. Caitlin, did you want to introduce yourself?
Hello, everyone. As described, I'm Dr. Caitlin Collins. I'm assistant professor at Virginia Tech. My background is in bone biomechanics, and I'm coming today to represent the engineering perspective.
Great. And then we have Dr. Sophie Verrier.
Yeah, hello everybody, and good luck to everyone. So I'm Sophie Verrier. I'm a principal investigator at the AO Research Institute in Davos. So for formation, I am a cell biologist, and I put a lot of interest in bone regeneration and also the impact involvement of vascularization therein.
Excellent, thank you. And then our next judge is Dr. Jerry Sang.
My name is Jerry Sang. I'm an academic orthopaedic surgeon in Oxford, and my interest is in fracture-related infection and impaired fracture healing. And good luck to everyone.
Awesome. Okay, and then our last judge is Madhura, who was our winner from last year's 3-minute thesis. So Madhura, do you want to say also your background?
Yeah, for sure. Hi, everyone. I'm Madhura. I'm a fifth-year PhD student in Dr. Joel Burko's lab at the University of Pennsylvania. I look at the periosteum and fracture repair, and I had a lot of fun last year putting together my 3-minute pitch. So I'm really looking forward to this year. Good luck to everyone that's participating.
Great, thank you. So as you can see from our judges, we have a wide array of backgrounds. So we have kind of the basic science, engineer, clinical perspective, as well as our trainee winner from last year. So we're really excited to have this kind of great group to do the judging today. So as I said, we'd like to also acknowledge the ISFR officers and other members of this committee and the staff who've been really critical to organizing the event today. So I'd like to give you a bit of background before we jump into this. The 3-minute research pitch competition has previously been a part of our section scientific meeting. It used to take place actually in conjunction with the ORS annual meeting in person. A few years ago, we held it virtually for the first time, and we've been continuing this today as it allows a lot more folks to participate from around the world. So really excited to have this again. The term 3-minute thesis, here's the 3-minute research pitch competition. It refers to the style and the focus of the competition rather than actually presenting a thesis or dissertation. So how this is going to work today, and as a reminder also to our speakers, each finalist will be given 3 minutes to present a single static slide that summarizes a significant body of work that they've completed or are currently working on. We will then have 2 minutes to answer one question from either you, the audience, or our judges. If you are unable to unmute, you can, of course, submit this over chat. We prefer if you do raise your hand. Unlike a typical poster or podium presentation competition that evaluates the project's significant rigor and hypothesis, in addition to the finalist presentation clarity and style, it's really a rapid fire competition where we're looking at the presenter's ability to convey the importance and the impact of their work in a really engaging and accessible way. So we're really using this to develop the skill sets needed to convey what we do to the public and those in other fields. We think it's a really important skill set for our field's future. And because of that, our winner today will take home a cash prize of $500, which is a great bonus as well. So very excited about today's finalists. You can see we have 6 very talented and diverse investigators that are all trainee members of ISFR. And with that, I'm going to pass them over to Mike, who can give some housekeeping before we get started.
All right, hi all. My name is Mike Hass. I'm a research assistant professor at the University of Pennsylvania, and I have the distinct honor of going through some of the housekeeping items that we have with you today before we get started. So just a heads up, everyone probably saw when they entered into the chat today or into the Zoom session, this is being recorded. For bandwidth purposes, if you're not participating, we ask just to maybe turn off your video if you think internet connectivity is going to be an issue. Please remain muted. throughout the course of the presentations that are provided. And if you have any questions or comments, when the time is proper, like you may kind of jump in and raise your hand on Zoom, and we'll do our best to have you ask a question. You can also put things in the chat that I'll be keeping after as well if there's no questions from the judges. We ask that you don't record this or take any screenshots as the information is being presented. You would need some prior approval in writing by the ORS, which we haven't received, so please refrain from doing that. And to enhance your experience here, perhaps consider using Speaker View so that you can kind of soak up all the science as best you can. So without further ado, we're going to get started. Our Peter Bertone from Dartmouth, and the title of his talk is Post-Radiation Renovation, Rebuilding Stronger Homes with Better Bones. Peter?
Awesome. Thank you for the introduction. So imagine you wake up one morning and you go to the bathroom and you look up in the corner of your bathroom, and then it's just the corner is missing and it's been eaten away by mold, and there's some mold spores kind of, eating away that corner of the bathroom. And typically the way you treat that, right, is you spray it with something. Well, you kind of cut away the mold that's there and you want to rebuild it and treat it so no mold spores grow back and sort of the problem persists. And you want to rebuild it to make sure the framework is good and the insulation is there and the plaster is there. Well, that's essentially kind of what happens in the bone from a primary or secondary bone cancer, right? That bone cancer comes in, you need to resect it, and then you treat it, and you typically treat it with radiation. So the goal of my research is to investigate and build a material that can work good work well and effectively in the context of regenerating and rebuilding bone that is undergoing treatment following tumor resection. So first thing, we want to build a foundation with the material. So right now I'm investigating cryogels. And what I did is I irradiated these cryogel samples with clinically relevant doses of radiation and then tested whether or not they were still effective at conducting osteoblast-like cells on their surface and throughout their system. And what I found was that our cryogels are still effective at regenerating tissue, bone-like tissue, after up to 21 days following radiation. Secondly, I want to create a material and incorporate things into our material that make it stiffer and stronger to be able effective in terms of give it structural support in the context of creating stronger better building blocks essentially. So what I've done is I've incorporated 3D printed hydroxyapatite cages essentially with our cryogel material to increase, and what we found is it significantly increases both its finally, I've been conducting a murine model, a critical segmental defect model in a mouse, where I've induced a critical defect, and then I'll fill that space with a cryogel then leave it as a control or irradiate it with these scaled clinically relevant doses of radiation to investigate what that regeneration looks like over 4 and 8 week time points. And what we found, as compared to the control as well as the defect that is left empty, following those doses of radiation, we're seeing clear bridging across that section of the defect, across that length of the defect, regardless of the radiation fractionated dosing regime, as well as compared to a control. And those are images there with the micro CT and the MRI qualitative images so far. So exciting stuff, and trying to essentially make the next building block to build back better, stronger bones following radiation therapy. So thank you.
All right, Peter, thanks so much. Anyone in the audience or judges have any questions? I'll start. I see here that your increases in Young's modulus are significant, but they're like orders of magnitude away from what bone is, right? So what's the plan to try to continue this upward trend in terms of a scaffold that can be like a little bit more load bearing, and you don't have to rely on like external fixation here or whatever to help there?
Great question. So far, I have been using plates and screws to sort of provide that that load bearing. So I've been including and thinking about including fixation outside of just the scaffold itself. However, something I've been testing in our lab is actually sintering. So treating our mineral lattices with high temperature combustion and sintering, and that is also significantly increasing its stiffness. So that is something that's getting us closer to that strength. Compared to at least cancellous bone, but we're not there yet. And I'm not necessarily certain because we can 3D print complex designs that could integrate well with fixation. So I'm not necessarily certain we want to bear a load entirely, but maybe get something close to being effective at sharing a load potentially. But that's what we're seeing so far, but that's a great question.
Great. Anyone else in the audience?
Yeah, I would. Hi. Very interesting thing, because that's true. Like as tissue engineer, we are always thinking like of reconstructing, rebuilding, and we do not think that the patient having like a tumor removed has to go also some radiotherapy or whatever, very difficult things, which would have an effect not only on the bone, but also on the reconstruction material. My question is like, what about the cells? Because usually when you put a biomaterial for reconstruction thing, then you would have to have some cells around. So did you like look at like the effect of that? Like were your cells more or less like destroyed, protected? Are there some kind of like shield effect of the material on the cells, or what has happened in the kind of like biological component?
Great question. So that in vivo model that we're doing now, I'm hoping is going to elucidate a lot of the questions you just asked, because ultimately, right now, this is just qualitative micro CT, MRI, and X-rays that I've been looking at. And so I think histology is going to give us a lot of that information, like what are the condition of the cells on the surface, integrated inside of the cryogel after 4 and 8 weeks following that radiation. And yeah, what are their condition? Are they healthy? You know, what types of cells are we looking at at these different locations? I'm really interested in seeing all of that. I haven't completed the histology yet. This model is still undergoing. With respect to maybe shielding of sorts, I've done a lot of material testing with radiation, and what I found was the cryogels that have been hydrated, so that are hydrated with water, they exhibit some shielding effects, both to its own properties, as well as the ability to then regenerate cells following that radiation. And there are cells still growing. I mean, you can see on the laying foundation image that those cells are really congregated towards the outside as well, sort of the edges of the rim of the material. So it seems like the material does shield it to some degree, especially when it's hydrated with some sort of fluid. So that's some of the early stuff I'm seeing, but I can't wait to see the histology, and I think that will help me answer some of those questions as well. But they're fantastic questions, so thank you.
Thank you.
So thank you so much to everyone. At this time, we're going to let the judges go into a breakout room and discuss the outcome of our competition today. So once that occurs, Anne will let us know, I believe.
I want to thank all of the contestants. You all did a wonderful job presenting your work in a very, very difficult format. So we greatly appreciate, all the effort and work you guys put in. It definitely made judging a challenge. We really appreciate all of your efforts. I want to thank everybody who's in attendance today. This is a really big event for us, and it's really important for the education committee within the ISFR to really highlight our trainees and try and increase engagement and involvement, and also spotlight all the great work that they do to support initiatives that are near and dear to our hearts. But without further ado, I'd like to congratulate our winner for today's competition, which is Peter Bertone. So we get a virtual clap. Congratulations to Peter. You did a wonderful job highlighting your work. The delivery was well done, answered questions very well as well, and overall performed highly. So it was close for a lot of you, but Peter came out on top, and like to congratulate him for job well done, and thank again everybody for attendance. Keep in mind, submissions for ORS are coming up. We'd love to see your work again, and there's opportunities for poster awards at the Phoenix meeting, and some highlights also potentially in the section meeting that'll be happening there too. So thanks again. I don't know if we have any other highlights Mike, before we wrap today. But thanks again, and appreciate all of your participation.
This is the last slide. Thank you so much to everybody.